morning from Miami Beach. It's Dr. John Bennett of Neurosurgical TV. Today we have the beginning of the intersection of neurosurgery and artificial intelligence. And we have Emrah Saltitsi from Turkey speaking. And first we'll introduce who's basically be the host. Hello, Isaiah. Go ahead, Isaiah. You are muted. Hello, Isaiah. You're muted.
No, she's dead. She doesn't want to answer.
Oh, okay. Maybe that's why. Okay, Isaiah, go ahead. Okay, well, I'll
hello.
Go. Yeah, go ahead, Isaiah.
Yeah, can you hear me?
Yes, we can hear you.
Uh,
You're gonna get fired the first day you show up late.
Sorry. First of all, thank you. Yeah. First of all, I want to express my deepest gratitude for Dr. Emrah Saltitsi. He's head of Department of Artificial Intelligence and Neuroscience. I have him here. Big data in neuroscience and neurosurgery.
Okay, I guess.
Am I the only one who is?
Yeah, you know, I was just going to say that. Okay, Doc, why don't you start? Okay, thank you very much. Sorry about the technical problems.
No problem. I think technical problems always happens. So I think you can see my screen and the presentation, right?
Yes.
So thank you, everyone. I'm Dr. Emrah Saltitsi from Gazi University Department of Neurosurgery, and today I'm gonna make a presentation about combining big data and AI in neurosurgery and its importance. Today I will perform this presentation with Dr. Umut Demirezan, who is a computer scientist in Digital Transformation Office in Presidency of the Republic of Turkey. So let's move on. So first, I want to introduce you Dr. Demirezan, our Chief Computer Scientist. He worked as an engineer lieutenant in naval forces in Turkey here, and he performed his graduate and doctoral studies, especially on the field of artificial intelligence and data science, big data, and cybersecurity. And before working with us, before working in a combined relationship with our projects here, he was working on swarm intelligence and autonomous systems, especially the drone technology. So as you will see, he is mostly into military technologies, but we transferred him into much more human subjects like medical sciences. So I'm very happy to work with him. And I'm Emrah Saltitsi, as I told you. I'm an assistant professor at Gazi University and Faculty of Medicine, Department of Neurosurgery. In my daily practice, I'm performing neuro-oncology cases, mostly endoscopic skull-base and glioma surgeries. And before my faculty position in here, I completed a research fellowship on skull-base in the University of Pittsburgh, under the supervision of Dr. Juan Carlos Fernandez Miranda. And currently I'm directing artificial intelligence and connectome labs in here. So, and that's me. So what's computer science? First, today we are gonna talk about terms like artificial intelligence, machine learning, supervised learning, whatever. All are in computer science. So if we want to understand what's going on with the artificial intelligence, how those algorithms work, and what's reinforced learning, what's the difference between a deep learning algorithm and a machine learning algorithm. First, we should understand the basics, and the basics comes with the computer science, which is not only about writing codes, but also understanding the mathematical basis of the artificial intelligence. So before starting my presentation, I'm planning something like 35 minutes or 40 minutes of presentation. I'm not like I'm not a long talker, and I don't like people who tries to tell too much things. So I'm gonna try to be brief, but there are lots of things to explain. So I recommend those three papers. First paper is my systematic review, which I wrote during my fellowship in Pittsburgh, because my first interest in artificial intelligence and computer science began during my fellowship days back in Pittsburgh, because we were working in a very close relationship with the computer scientists and other guys. So this paper in 2018 became one of my most cited papers, and so I recommend that paper. And the second paper is written by Sandeep Panesar, who is a friend of mine, and we performed fellowship together. And so that's a really great paper explaining what's expecting us, what can we do with the artificial intelligence, and especially in neurosurgery, and what should we expect and what should we not expect. Also, there is another systematic review on natural and artificial intelligence in neurosurgery. Also, I recommend this paper. So these are three basic papers of my recommendation. If anybody is interested in what's going on in the field of artificial intelligence, especially in neurosurgery, those are my recommendations. So the growing data on artificial intelligence is increasing in a logarithmic way. So the radiology journal, they had so many artificial intelligence papers that they start to publish a secondary journal called Radiology Artificial Intelligence, and it started in January 2020. So we can understand this. The field is especially very active on the last 10 years, but especially in 5 years, because the technology is developing not only in the CPU technology, but also in the technology of graphic processing units, GPUs. So that's something very important if you are working with huge amount of data, including images, and if those images are high quality, then you need a great amount of GPU. So let's go to the basics. So what's a sigmoid function? A sigmoid function clearly defines, as you see here, on the x-axis is our input. So our input is, it could be anything. It could be blood pressure, it could be something else, it could be the survival, whatever, but our results are mostly binary. So it's true or it's false. So let's say it's 1 or 0. So a simple sigmoid function defines a very basic of the artificial intelligence, machine learning, and how it works, but it's just basic, just for explanation. So how it works? So let's assume that we trained our data set with four different inputs, and all of them has different results. Like here it's true, here it's false, here it's true, here it's true, whatever. So basically the algorithm will extract the data, and maybe it depends on your architecture of the algorithm you're using, but there will be a secondary result, and then you will have a final result, which in here the last curve here defines the result of your artificial intelligence. But what's the difference between artificial intelligence and the simple linear regression models? Because we all know, as the neurosurgeons or medical professionals, we are mostly based on using linear regression models, simple statistics, and they are especially based on regression models, linear regression models. So what's the difference? So here on the right side, you will see a regression model showing the relationship and showing the true and false, what's true, what's false, what's close to the line, that which is the function you defined. But a classification model, which we will talk later, what's a classification model? A classification model is something more than a linear regression model. It's something very dynamic, which changes every time you feed with a new data. So the upper part of the curve and the lower part of the curve could change anytime with your feedback, with your improving data. So a classification model is something much more dynamic than a regression model. So there are lots of algorithms which are supervised, which are unsupervised, like decision trees and logistic regression and support vector meshes. There are lots of in literature we will talk about support vector meshes, especially most of the papers are coming from logistic regression, support vector meshes, especially supervised models and unsupervised models. There are lots of clustering algorithms, whatever, but today we have very limited time and we cannot talk one by one what those algorithms, they're just examples, what those algorithms and what are they working for. But there's always a question people are asking me, so what's artificial intelligence? They can understand, but what's the difference between a machine learning model and a deep learning model? So here, machine learning models are mostly working with training with known outputs and features. So there's a feature selection which is performed by a human here in our case. But the deep learning algorithms could develop their own data classifier. I will explain later what I mean. But again, remember my previous graphic, which is defining a classification model. So all you need in deep learning algorithms simply is raw data and output. It's not that simple, but that's the summary. So here we can see how the workflow is working in most of the cases. So we have an input and we have a method. I will tell what the method here means. So we will have a feature selection. We can do this, or the algorithm can do. So we will have a classification model, or we will not. It could be hidden in the layers, like a deep learning model, and we will have an output. So especially if we have a look at the machine learning workflow, we have an image, which is an input. It's raw image. So then the human performs the parameter selection. So which is an abnormality segmentation. We can give an example in this case, and segmentation of a normal anatomical structure. So that's the parameter selection. And then classification. We keep training data set with those kind of data. What's abnormal, what's normal, anatomical variation, whatever. So we produce here a classification model. And then we will have an output, so which will show you in it's never 100%, of course, which will show you what is wrong and where is not what is wrong, but where is wrong, especially in image processing. Where is the problem? So that's one of our patients that I will show you during the speech. So here, okay, that was machine learning, and now deep learning workflow we'll talk about. So we have an image, which is the input layer. Again, we are talking about image processing, which is better, which could be better understanding. That's my opinion. So there's a hidden layer. So what the hidden layer means, the algorithm itself selects the features, makes the classification, and produces a classifier algorithm, and then it makes an output. So that's again one of our studies I will mention in the in this presentation. So that's basically a very simple explanation of deep learning. So let's come back to the neurosurgery. So what's going on in neurosurgery? Current trends are mostly in decision making, image processing, and brain-computer interface. So those three aspects are very important. That's I don't know, maybe that's my only opinion. One can say, oh, what's the thing about brain-computer interface and neurosurgery? But we will see what's going on. So in decision making, there are lots of applications we can perform, like treatments and complication prediction, outcome prediction, survival prediction. So let's take a look to the literature. So here, as you see, it's a paper from 2017, automatic detection of subthalamic exit during deep brain stimulation surgery. So those guys from Israel performed their decision-making algorithm by using their data set on especially Parkinson patients, and performed automatic detection of subthalamic exit, which is available, as you know, normally is performed by, especially in our department, is performed by a neurologist who keeps on tracking the microelectrode recording. But this paper shows an artificial intelligence method could perform it as well as human. Another paper from neurosurgical focus, factors triggering and additional resection and determining residual tumor volume on intraoperative MRI. So in this paper, the authors found that machine learning prediction model was applied to consider if anticipation of intraoperative findings permits preoperative identification of ideal intraoperative MRI cases. So this is basically showing, especially in surgery, in this paper, authors are explaining, especially during surgery, we all know we are neurosurgeons and we have a, you know, at least even our humblest ones are have a little level of ego. So we will say, oh, okay, I did resect all the tumor or whatever, but the machine learning prediction is better than human prediction, because what does a computer, what does not a computer have is emotions and ego. So they always decide what their algorithm says. Another paper, which I think very old paper, but a very good one, which is the forecasting ICP elevation based on changes of intracranial pressure waveform morphology. So in this paper, authors found they can predict an incoming ICP elevation 5 minutes before, just making a prediction from intracranial pressure waveforms morphologies. It's probably it's possible for humans, but you know, you must dedicate your life and just follow the patients, what's going on, and when the ICP will increase and when not. It's also our brain works in a way of machine learning and artificial intelligence, but for a computer, it was really high specificity, with a high specificity, 97%, and it was able to predict there's an incoming ICP increase just 5 minutes before. So let's talk about complication. This paper from Journal of Medical Imaging, image-guided preoperative prediction of pyramidal tract side effect in deep brain stimulation. So another paper, support vectors classifier to approach predicting the risk of progression of adolescent idiopathic scoliosis. And in this paper, authors demonstrated that it took less than 20 minutes per patient to measure the indicators, input their values into the system, and produce the needed results, making the system viable for use in a clinical environment. So these authors are telling 20 minutes is not for the computer, is for the human to enter the results. And for computer, it's probably just less than a minute. So predicting the risk of progression of adolescent idiopathic scoliosis could be done by a computer. So outcome and survival. Everybody is asking this to me. Is it possible to predict outcome and survival? And I always say yes, because there's a huge amount of data, not only in the literature, but also in hospitals you're working in. So you only need is data, and you only need is to classify correct data, and you even don't need most of the time molecular biomarkers, whatever. They will increase your they will increase your prediction level, but it doesn't mean without them you cannot perform any predictions. So etiology, age, great plexus, catheterization status, type of hydrocephalus, and they implemented this in an artificial neural network analysis. That's in my opinion, that's a really great study. And compared with ETV success score, which we are still using in our pediatrics team is using this score, or Cure Children's Hospital of Uganda score and ETV success score, the artificial neural network models in this paper showed better results for predicting the endoscopic third ventriculostomy. So that paper is really good, which I strongly recommend all of our participants to check this paper, because in this paper, authors use the brain connectome as a personalized biomarker of seizure outcomes after temporal lobectomy. So in this paper, the model combining clinical data and neural network architecture demonstrated a sensitivity of 82% for seizure freedom. And here I want to open a parenthesis. The brain connectome itself, which we are also working in another lab here, is something else. I didn't add connectome analysis, graph theory analysis, or what's a small world network in this presentation, because in my opinion, it's a whole at least 45 minutes talk. But if you are working on connectome analysis based on graph theory, so my recommendation for everyone to read what the graph theory is. So basically, I will explain here what a graph theory is. A graph theory explains, for example, let's talk about the domestic flights in the United States. So in United States, if you want to fly from New York to, let's say, Austin, Texas, maybe you can find a direct flight, but if you don't find a direct flight, probably you will make one of your destinations will be, for example, Chicago. So why there are some hubs and there are some nodes? Because that's very efficient. You cannot connect every single place. You cannot connect every single flight to everywhere. That fact is the same for human brain. So human brain shows high effectiveness, which means Also our brain is like airway routes. It tries to work in a more efficient way, doesn't connect every single point with every single point, because that's not efficient. So even in this form, it's consuming a lot of oxygen and energy. So if we want to make an analyze, a graph theoretical analyze from the human connectome, let's say from tractography studies, we strongly need big data analysis and big data analysts. So that's the thing that I'm gonna end here, because as I told you, graph theoretical analysis of the human connectome is another big world, and we doesn't have enough time here. So and again, outcome and survival, generic support vector, machine model for preoperative glioma survival associations. So especially, probably you guys heard about gliomics or radiomics especially. So I will talk about this later, but simply the machine learning models or deep learning models could see patterns which we cannot. A computer could easily see what's going on with a glioma, or if it's IDH mutant or IDH wild type, whatever. But most of the human cannot, because we cannot analyze pixel by pixel, but the computer can. So that's the advantage of artificial intelligence, especially implementing artificial intelligence in image processing, which we also working on. So here they trained their data on 101 patients from the first institution which they gathered their training model, and they tested their support vector machine models on independent data from another 134 patients at the second institution, and they found whole tumor perfusion parameters based support vector machine model are the strongest parameter associated with predicting the survival of glioma. So another paper for outcome and survival, again with the glioblastoma, which is telling simply individual glioblastoma molecular subtypes with an overall accuracy of 76%. So I don't know if you guys ever know human who can predict every single molecular subtypes of a glioblastoma just by looking to the MRI. It's not like predicting dark flare sign for I don't know diffuse gliomas, but I mean every single molecular subtype detection for human eye is not that easy, but the machine learning techniques are available, and they can produce acceptable results for this kind of predictions. So we talk about clinical applications of the machine learning, and our second chapter here is the brain-computer interface. It will be a short chapter here, but that's brain-computer interface and artificial intelligence is very important, especially guys, maybe you all saw on TV the Elon Musk and his team is working on pigs, which is basically very similar to a Utah array, and so brain-computer interface studies. That's my strong belief, will increase in time. What we need, especially in those studies, is not computers or algorithms, but we need much more precise nanotechnology development, which will be effective and safe to implement arrays like Utah array to the human cortex. So this paper is very important. There's also a video on YouTube of this lady. This team was in University of Pittsburgh, and I had the chance to met this lady just outside of our lab, and she was something like 10 years of tetraplegic, but she had an intact motor cortex, and they implemented a Utah array on her motor cortex, and by this she was able to eat her first chocolate after 10 years with a prosthetic arm, which she can use. So the brain-computer interface is a little different from other artificial intelligence models. Here is why. So in brain-computer interface models, if we are working with invasive techniques like Utah array, simply the Utah array gets the data from the cortex, and the data is simply like a EEG, but for the algorithm it's always binary, and the algorithm keeps training with the feeding data. It's like, okay, move along, or move your finger, whatever. So it could move the prosthetic arm. But the thing in here, I mean, if we were talking about image processing, it was over in here. But if we are talking about brain, in this model, there is not only one computer, but there's two computers. First computer is, of course, the computer that extracts the data, but also our second computer is the brain itself, because it's like learning how to use a prosthetic arm is like physical therapy. When a patient loses the ability to use his arm or leg or whatever, they perform a physical therapy. A physical therapy is not only you know, making strong muscles or strong bones. It's not this, but also retraining the motor cortex, retraining the supplementary motor area. So it's machine learning again. It's not artificial, but it's intelligence itself. So let's say natural intelligence. So the brain-computer interface itself is a challenging point, and I find it really interesting. I'm pretty sure invasive techniques will improve in time, because as I told, the people working for Elon Musk is still working on this project. But also there's a way of non-invasive brain-computer interface other than Utah array or other things, which is the EEG itself. So in our lab, we are also working on some simple EEG projects. It's a very new area for us. Here you will see a drone, of course not an actual drone, but a simulation. So our subject here tries to use his cortical activity to fly this drone and to land it. So this data is extracted from a very simple 10-channel variable EEG cap. So we were able to perform this. So as I told you, non-invasive EEG methods are also available to work for the brain-computer interface. But here, before finishing this topic, I want to tell, if you are working on EEG, which is non-invasive, there will be too much noise. And if you are working with too much noise, it will be harder to train your algorithm. But if you're working with invasive methods, the amount of noise you are struggling will be lower, so your results will be better. And our last chapter, which most of our workforce is implemented on, is the image processing. So as you will understand, image processing is the part which is really important in the future, because as you will see, I will show you some examples, but let's assume a feature that they find the RNA vaccination for glioma, because they already find a huge amount of funding following the COVID-19 disease, the vaccination companies. So let's assume that this pandemic created a huge fund for those companies, and somehow they found vaccination for glioma. So what will we need then? We will need just a biopsy. So what if an image processing based artificial intelligence algorithm, a deep learning algorithm, tells you what the tumor is and what the genetic or molecular biomarker about the tumor is, then you will need basically no biopsy. So probably some of the neurosurgeons will be unemployed, God knows. So the basic is radiomics. This paper is very important, and this paper itself is the paper which drive me to get into this field, because following reading this paper, I found that, oh, okay, if things are going like this, there's a chance of performing no glioma surgeries, or at least a little part of it in a time, and I'm very young, so if I'm gonna see it, I should be a part of it. And I strongly recommend this paper for everyone to read. What's radiomics? In this paper, basically they are telling, as they are telling in the title, images are more than pictures; they are data. So so what's data? What's the power of data? Here I'm gonna tell you, and let's talk about my country. So in the Republic of Turkey, here we have a universal healthcare system. So which means government covers nearly all healthcare fees for its citizens, and the examination prices are really cheap because they are not private. I mean, you can go to a private hospital, of course, but the government prices I'm talking about, it's nearly currently $15 a whole brain MRI. You can in my institution, you can take a whole brain MRI in a Siemens 3 Tesla device, and including everything, perfusion, spectro, whatever, and probably it will not cost you more than $100. So also because of universal healthcare and cheaper examination prices, there's a very high hospital admission rate per capita. Let me give you an example. In recent years, population of Turkey is something like 80 million, and admission to the emergency services in just 1 year was like 110 million, so more than the total population Which shows us there's a huge data, huge amount of data collecting in our databases, and we should use it because a single data doesn't have too much value, but data of, let's say, 5,000 glioma patients is something. If you're working with big data, if you're working with image processing, or if you're working in, outcome prediction, or in an algorithm like I'm gonna show you. So let's check the number of MRI units. Those are 2015 numbers. I can't find those numbers, but I'm pretty sure they didn't change that much. So in MRI units, we have something like 10 MRI units per million. And for CT scanners, we have 14 CT scanners per million, which is below the OECD mean numbers. But let's have a look. As you will see, per 1,000 population MRI exams, Turkey has the highest numbers. So it's very simple because it's universal healthcare. It's very cheap, and most of those MRI exams are brain, lumbar spine, cervical spine, and knee and shoulder, but nearly half of them are neurology related MRI exams. So you can imagine now, I think, the amount of data being collected in every single hospital in here, and that's why I created this idea. We are working on we are sitting on a how can I say oil field. It's raw. It's nobody worked on it before, but it's like an oil field. The oil field here is the medical data. We have huge amount of MRI data in everywhere you can. You can easily find MRI data if you are working as a doctor in a hospital in here. Also the same for CT scans. So here you can see a number of CT scans per 100 population. So we have huge amount of data. We are doing nothing with it. So we had an idea, okay, we could work with it. So then we started a project called Turkish Brain Project, and we implemented 3 different labs in 3 different institutions. 2 of them are in Gazi University, and one is in the Digital Transformation Office of the Presidency of the Republic of Turkey. So the presidency itself is funding us for the next 2 years. Aim of the project is very simple, in fact, to produce a CT and MRI based early warning system and to generate value from intensive data. So before working on this project, we start to work on what can we do with our data here. So first, we worked on T2 images, and we gave this data to our engineers, computer scientists in here, and asked them if you guys can tell us the difference between a normal and abnormal image. And we found that accuracy rates was really acceptable. So then we said, okay, let's create a deep convolutional generative adversarial networks for automatic segmentation of gliomas. So difference from the previous study, in this study, we trained the algorithm just with the normal data. We didn't implement any abnormal data, and we used 2 different data sets. First data set was the BRATS data set. Probably most of you guys know it's an open access data set, and it's mostly based on glioma research, which it's accessible. So here you can see in every step the algorithm is learning. Algorithm is learning and telling us what it learned. In first images, you can see the MRI slices are not that good, but when we keep algorithm training, it creates more better synthetic images. Those images belongs to no one. They are just synthetic. Oh, sorry. I'm deeply sorry. There was a problem. Okay. And now, but we had a problem with Brat's data set because the quality was not sufficient for us. So we said ourselves, okay, why don't we create our own data set? We have a huge amount of data here, and we created our own data set. And here, it's created from a part of the Gauzy data set. You can see algorithm is creating in every step better and better synthetic brain images. And at last step, you can see the brain images are really acceptable. And in most slices, I'm not talking about posterior fossa because you will see it's not that good in posterior fossa. But if we are talking about the slices in where we can see the ventricles, it's really hard to define if this MRI belongs to a real man or is just synthetic. So here you can see MRI images and you can see how a deep convolutional neural network learns from normal images. So our next step was, as you can see on the right side, when we give a real person, which is a normal person, and we ask the algorithm, okay, create a random image, not random, but create an image which is similar to this, but from your from how you learned before, and it created an image. Here you can see, and on third column you can see the error map. So here error map is not that bad because that was a normal person, normal subject. But on the left side here you can see this patient has a tumor, has a cystic tumor on left temporal side, and we asked the algorithm, okay, create an image which could match with this person's slice. And following this, algorithm told us with this black area here, algorithm is telling us this this is an error. So for an algorithm, there is no patient, there is no disease, there's an error or there's a segmentation, whatever. So by this way, we find out we can teach an algorithm just what is normal, and also we can extract data by creating just synthetic images, and we can ask the algorithm to compare those images and tell where the error is. So in this way, algorithm find the cyst or the tumor itself. So the workflow here is in our project. First, we extract the data, the DICOMs, and we anonymize them. And following anonymization, we have a data labeling lab in here. Our guys are labeling every single slice. What I mean here, now currently on MRI study, we are working on axial images only because algorithm doesn't need sagittal or coronal planes. It's for us, for our three-dimensional understanding. Our algorithm is working on axial images only, which are T1, T2 weighted. and dark fluid, which is flare. If there's any T1 weighted contrast enhanced images, and also we are now adding the diffusion images, because we also want to implement stroke patients, not only the other patients, but also the stroke patients, everything detectable with an MRI. So by performing labeling, our guys in our lab are performing labeling like this. So in a MRI slice, they are labeling the region of interest first, because we find that what we first teach an algorithm is the region of interest. So where it should look. This provides, sometimes you can see some noise around MRIs, and this could be understood as an error by the algorithm. But by labeling the region of interest, we are trying to make a stop for this. And also we are labeling the orbit, also the eye, the optic nerve, ventricles, and the cerebellum, and other cranial, intracranial, let's say, anatomical structures. So following the labeling, we perform a 3-level of quality control, because following the labeling, one person makes a quality control, then another makes a quality control, another makes a quality control, which increases the effectivity of the labeled data set. And now, following this, we have a labeled data set, anonymized and labeled data set, and we perform a training of the algorithm, of course. And following the training, we perform a test with a test set, not in real life, but a test set, which we also created for testing. And if our test results are acceptable, we make a fine-tuning and adjusting for hospital PACS system in order to test on real life data, on real fields. So fine-tuning here is very important, because let's say you can work on a Siemens MRI device, or a GE MRI, or a Philips, whatever. Their metadata labels would be different. Some would say flare, some would say dark fluid. So there's a need of fine-tuning, because algorithm will extract the data what he needs only for testing the real data, which I will show you as a real demonstration. So basically, algorithm here, everything is in Turkish, but it says the result of the analyze took 20 seconds, and there is no abnormality here in any slice. So here shows our explainability map. Currently, we have 2 different algorithms working together to make a decision. First algorithm tells you the explainability map. So here, explainability map is also for us, I mean for human, for medical professionals, because I want to learn if the algorithm is telling something wrong. I should know that is it pointing the right spot, or just by chance. So I have to understand what's going on. So how explainable map works is, here the red area shows the region of interest. This is a real life patient which algorithm found, but as you will see, this patient had a decompression, decompressive craniectomy previously. So I'm not interested in decompressive craniectomies, because it could be, it's not an abnormality itself, it's the result of a surgery. But what I want to find is if this patient, even though the brain is decompressed, if there is any abnormality in here. So you will see what the abnormality is. That's an abscess formation, and it's showing us the explainability map is showing us what's wrong in here. So that's our second model, which is the object detection model for the same patient. And it's showing us the object itself, it's segmenting it, and those two models are working together in order to tell us what's going wrong. Also, we created a system. When those two models agrees on an abnormality, it's sending a text message to my phone and telling, okay, Emrah, check this patient. And it's also sending a GIF image showing the MRI of the patient. And then I can have a look even by the standard PACS system of the hospital or our own PACS system, which is working based on machine learning, artificial intelligence algorithms. So sometimes our algorithm finds some abnormalities on MRIs, which we never trained before, like this patient. As you will see on axial images, this patient has tonsillar herniation. In fact, this patient is a Chiari type 1 patient. And algorithm find out there's something wrong with the cerebellar tonsils in here. Or like this, we never trained our algorithm with, venous telangiectasis or something else like this. But algorithm finds there's something wrong with this patient. And it's telling us in 5.5 seconds and telling us which slice it has. So I try to keep it simple.
In the last paper that I was interested in that, and I really thank you for explaining about that, was about GAN. GAN, as you know, is a precious, one of the best techniques in deep learning, and actually the newest one. And I didn't just figure out you used GAN for augmenting data. Yeah. You just augmented your data by GAN?
We're using data augmentation. In that paper, yeah. We also used data augmentation both by using GAN and by using
algorithm
random flipping.
Yeah, that's great. And can I ask another question about your application?
Yeah, sure. I'm listening.
Yeah, that was a great. So that was a great application. Just I didn't know that you every time you add a patient to your application data. Yeah, to your data.
Are you asking for training or testing?
Every time that a patient. For training, because in these kind of applications, people add new people and they use reinforcement learning. Yeah, you use reinforcement learning for the application.
In fact, what we perform now is we are trying to figure out which patients, not patients, but which normal subjects are labeled by the algorithm as a patient, not a normal subject, but as a patient. We extract their data, we label them again, and we use this data in new training models. We are always trying to extract our data by using now especially false positive cases.
Yeah, great.
Because currently we have a real acceptable level of sensitivity. It's something like 98-99%. because we put the threshold really high, but the specificity levels are a bit lower. I want them a bit higher. Our specificity levels are 75, 76%, and I really need specificity levels over 90 or 92%. So if I want to decrease false positives, I need to teach the algorithm with the false positives.
Yeah, because as you know, for example, some net in Google are like ResNet, because of just it is a huge network, and it would be precious. That way, it was a question for me. Your network, how much is big, and yeah,
Okay, we're ready to move on.
Okay,
thank you.
you're welcome.
Okay.
Thank you for that.
Sorry.
Thank you.
You're welcome, and thank you
is,
too.
Yeah, this is part two. Part two.
Okay.
Okay, we're waiting for someone to speak. Can you introduce your partner, Emra, please?
Excuse me, I didn't hear you.
Can you introduce your partner, please?
Oh yeah, Dr. Umut Demirezan is here, I think.
Yeah. Hello. Thank you very much. I am very happy to be with you. I'm sorry with the slight delay. I cannot hear you at the real time. Sorry for my late reaction. First of all, deep learning is a good technology, but it's not a silver bullet for every problem resolution. So the main idea is we want to discover some kind of unknown patterns, even by doctors, and investigate the results. We only gave the algorithm just an image and a label. The label quality is the most important part of the algorithm development. So garbage in, garbage out. The concept is very easy and very simple. So if you represent your data, represent your domain by high quality data, you don't have to extrapolate. The only thing is you are doing an interpolation mathematically. But as for your question, as my colleague explained for the paper, data augmentation is some remedy, but the resolving by using the GANs, it provides some remedy for the problem, data scarcity. But the main aim is that work is teaching the artificial intelligence what is the brain, what is the parts of the brain related to investigation, and what is the normal brain. So if you ask it after the training, what was your best guess if I gave you this image and if I gave you the slice number, you could give me the best matching MRI slice or CT slice by using this information. Then you compare the things between the normal and the abnormal, the target data, and you can easily decide whether or not it is a good slice or an anomaly included slice. But the other question, our architecture is not big, not so much big. It is not. It's based on the Occam's razor, right? If we can keep it simple, the model cannot be highly complex. We can extract some feature by using the deep learning hierarchy, because convolutional neural networks or the segmentation algorithms learns everything in a hierarchy. So it learns from the basic shapes, circles, lines, points, then the more complex polygons as engrams, this kind of complex things and finally it decides whether or not it's a good slice or the anomaly included one. So the main reason is we taught the algorithm just only the necessary brain parts, not skeleton, not skull, not synaptic things. We only taught the algorithm just if you know, if you see anything, a bad shape, unusual shape, and if you detect any unexpected fluid around it, it can be an anomaly for us. But it includes really hard parts, because the most important places in the brain has to be investigated hierarchically. So ResNet is a good architecture, UNet is a good architecture, but our solution is based on a novel type of algorithm. It is based on both unitish or convolutional network based algorithm.
Excuse me, Umar. Excuse me, Umar. Do you have slides you're showing? We're not seeing anything. Did you have a presentation or slides?
No. His is just.
Oh, okay. I'm sorry.
I'm just answering the questions.
Okay, I'm sorry. Okay, sorry to interrupt. Go ahead.
Okay, thank you. So this kind of architecture can both investigate the subject, the patient, slice by slice, and also gives a much more capability to find multiple things, multiple anomalies at one time. So it requires a different architecture than the ResNets. It requires a different kind of approach to the UNet or segmentation networks. So we try to bind it all together. Also, we tried multiple type of algorithms at the same time. So when our algorithm gives good results, like 2 or 3 different doctors gives their opinion about the MRI slices. So their decisions, 3 different algorithms decisions come together and fuse the results and gives more accurate answers for them. So the main part of I'm with the same opinion with you. Explainability. They seems like a black boxes, but in the recent years we have lots of technological development and research about the explainability of the AI. So we place that kind of technology, that kind of solutions to our product line, and we applied that kind of technology to our system, and we see that it's really good thing to use explainability to discuss the results with the doctors. The most important thing is, my colleague has reported 98–97% of accuracy for anomaly detection or other tasks. He means that it gives you the real results, not on the limited type of test set. He gives you the real life data. So we can induce our results 100% accuracy specific data set, but it's not enough, because this is not the case. We test all our systems all around the hospital, maybe 6 or 7 different MRI machines with different kind of people, with different kind of patients. These reported results comes from the real scenario, real world data. This is the most important part. I want to emphasize it again. Sorry about it. Thank you very much. I hope I can answer all your questions.
Thank you so much for your explanation and your answering. It was so precious for me.
Thank you. It's my pleasure.
And anyone Okay.
Okay,
Okay,
Emra,
Dr.
what would you
Omar.
like to do, Emra?
I'm gonna visit my patients following this presentation. Yeah,
Okay.
in the morning, I just operated a chordoma patient. So
Oh, wow.
research is going on and surgery is going on. So if you want to collect more data and make a cumulative data set, we should keep on working and tracking on our patients.
Okay. Thank you so much, Dr. Emre Siltik.
Yeah.
And
That was a pleasure. I thank you.
Okay, very good. I guess we'll wrap it up. Thanks, Azadeh, and thanks everybody for coming, and Umit, and the rest of the crew. And we hope to have more webcasts with you, because as you
Yes.
know, we're trying to stimulate the interest in the general neurosurgery community in artificial intelligence, because we all know it's got a great future. We don't know what, and we'd like to have